Hello everyone, my name is Stephen Gigrich, and this is Lab 4, Circuits. As an overview of my lab report, I'll first introduce the lab and the physical principles behind it, as well as go over my lab setup. Then I'll go over my lab procedures, observations, and I'll end it off by answering the two questions of the main ideas of the lab. Introduction. Background information and physical principles. Ohm's law states that the voltage of a circuit is related to the current and resistance of that circuit, in the relation that voltage equals current times resistance. Conventional current is the direction of flow used by convention where positive charges are flowing. Electron flow is the actual way that the current flows, where negative electrons are mobile. Electron flow is equal to the negative of the current flow. Kirchhoff's voltage law, also known as the loop rule, states that the total sum of all voltage changes in a closed-loop circuit excuse me, is zero. Kirchhoff's current law, also known as the node rule, states that the total current entering a node in an electrical circuit is equal to the total current leaving that node. The purpose of the lab experiment was to increase our understanding of the behavior of ohmic resistors and capacitors, and be able to predict how the circuits will run both in series and parallel. A secondary purpose of this lab is to get more practice using voltmeters, ammeters, and multimeters, and the common elements of circuits, such as resistors, batteries, and capacitors. Here's my lab setup during the experiment. In this image, you can see a circuit consisting of a battery. It's two 1.5 volt batteries, so a 3-volt battery, and two resistors, a 47 ohm and 100 ohm resistor. You can also see the multimeter being used within the circuit. Here's more of my lab setup where we can see three more circuits. The leftmost circuit contains a battery, a light bulb acting as a resistor, and a capacitor. On the bottom right, you can see where we are timing the charge time of the capacitor, and then the top right, you can see how the light bulb is being powered purely from the capacitor and no battery. Here's our gathered data and a graph showing the voltage change over based on the position where we are measuring. You can pause here and take a look at this data. It's pretty interesting. For the system and surroundings of my lab, the system of the experiment was the resistors, capacitors, batteries, wires, lights, and the multimeter. And then the surroundings of the experiment was the room in which the experiment was conducted and all other circuitry present in it that might affect the readings. A preview of my experimental results is that Kirchhoff's voltage and current laws both hold true, Ohm's law holds true, and that capacitors can act like batteries and are pretty cool. Lab procedures/results. To conduct our first experiment and build our first circuit, one, you need to acquire the necessary materials, which would be two 1.5 volt batteries, one 9-volt battery, a 47 ohm resistor, 100 ohm resistor, and 30 ohm light bulb, and a 200 millifarad capacitor. Set up the circuit containing two 1.5 volt batteries and the two resistors, 47 and 100 ohms, respectively. Measure and record the potential difference across the resistors using the voltmeter, and then measure and record the current across the resistors using the ammeter. Some observations I had during the lab were that the current across the circuit remained the same, and that we measured that at 0.02 amps. Yeah. Another thing was that the voltage drops across resistors, including light bulbs, which can act as a resistor, and that the voltage across an ammeter remains the same, which would be 0. To continue my observations, in the capacitor circuit, it took 1 minute and 20 seconds for the capacitor to charge when connected to the 5 ohm light bulb and the 9-volt battery, and it took 1 minute and 14 seconds for the capacitor to discharge when powering the 5 ohm light bulb. Some possible sources of error include a faulty voltmeter, faulty ammeter, bad readings, a bad battery, inconsistent resistors, and a non-ideal circuit. Questions and answers. Some assumptions I had were that the resistors acted as ohmic resistors, that the copper wires have no resistance, there's no loss of current over time or distance, and that all the measuring devices were accurate. To answer the first what if question, if we instead did this in a simulation where everything is idealized and perfect and there are no losses, then we would have a different reading than the real life thing. It probably wouldn't be that far off, but it would just be more precise to that simulation. And it also changes because uh, in the simulation, it's impossible to read or hook up the voltmeter and ammeter wrongly. To answer the second what if question, the measured time would be different than the predicted time due to losses of energy through heat. This would cause the capacitor to charge more slowly and therefore take longer than the simulated time.